What if the secret to revolutionizing quantum computing has been hiding in something as simple as sound waves all along? A groundbreaking discovery from California Institute of Technology researchers is about to shake up everything we thought we knew about quantum memory storage. But here's where it gets controversial. While tech giants pour billions into complex quantum solutions, a team of graduate students might have just cracked the code using what's essentially a microscopic tuning fork. Alkeem Bozkurt and Omid Ghalami, two determined graduate students working under the guidance of Professor Mohammad Mihosseini at Caltech, have pioneered an innovative hybrid approach that's turning heads in the quantum computing world. Their research, recently featured in the prestigious Nature Physics journal, unveils a system that does something many thought impossible. It converts electrical information into acoustic vibrations to preserve quantum states for dramatically extended periods. And this is the part most people miss. Their method can maintain quantum information for up to 30 times longer than conventional techniques. Think about that for a moment. In the quantum realm, where information typically vanishes faster than you can blink, these researchers have found a way to make it stick around long enough to actually be useful. Here's how their ingenious system works in simple terms. Picture a superconducting qubit, the basic unit of quantum information, sitting on a computer chip, connected to what scientists call a mechanical oscillator. This oscillator is essentially a miniature tuning fork that vibrates with sound waves at incredibly high frequencies. We're talking gigahertz range, billions of vibrations per second. When electrical charge hits the oscillator's plates, something magical happens. It can capture and interact with electrical signals that carry precious quantum information, allowing that data to be stored and later retrieved on demand. But here's where the controversy begins. Why sound waves instead of the electromagnetic approaches that dominate current research? The answer lies in physics that challenges conventional wisdom. Acoustic waves possess several game-changing advantages that electromagnetic waves simply can't match. First, sound travels significantly slower than electromagnetic waves, which means you can pack much more information into a smaller physical space. Imagine fitting a highway's worth of traffic into a country road. Second, and this might be the most crucial point, acoustic waves don't propagate freely through space like their electromagnetic cousins, which means the precious quantum information stays locked inside the system instead of leaking out and disappearing into the surrounding environment. This breakthrough directly tackles one of the most stubborn challenges plaguing superconducting quantum computers today. Traditional superconducting qubits are incredibly fragile. They lose their quantum properties almost instantly, making it nearly impossible to store quantum states long enough for complex calculations or logical operations. It's like trying to write with disappearing ink that fades before you finish your first sentence. The extended lifetime achieved by these mechanical oscillators represents more than just an incremental improvement. It's potentially a paradigm shift. The researchers believe their platform could be the key to creating truly scalable quantum memory systems by incorporating multiple oscillators onto a single chip, essentially creating a quantum storage array that could revolutionize how we approach quantum computing architecture. But here's what makes this discovery even more intriguing and perhaps controversial among quantum computing purists: the simplicity of the approach. While other research teams are building increasingly complex systems with exotic materials and extreme conditions, Bozkurt and Ghalami have demonstrated that sometimes the most elegant solutions come from thinking outside the conventional quantum box. What do you think? Could this sound-based approach be the missing piece that finally makes practical quantum computing accessible to the masses? Or are we still decades away from seeing real-world applications? And here's the million-dollar question that's sure to spark debate. If graduate students can achieve such breakthroughs with relatively simple acoustic systems, What does this say about the direction billion-dollar quantum research programs should be taking? The implications extend far beyond just academic curiosity. If this technology can be successfully scaled and commercialized, we might be looking at the foundation for quantum computers that can actually maintain their quantum properties long enough to solve real-world problems, from drug discovery to climate modeling to cryptography. The research team has made their complete findings available through Caltech's official announcement and the detailed technical paper published in Nature Physics, offering unprecedented transparency into their methodology and results. What's your take on this acoustic approach to quantum memory? Do you believe sound-based quantum storage could be the breakthrough that finally brings quantum computing into mainstream applications? Or do you think there are hidden challenges that these initial results haven't revealed yet? The quantum computing community is watching closely, and your perspective on this potentially game-changing development could contribute to the ongoing debate about the future direction of quantum technology research.